So last time we kind of went over where the Bode plot comes from, and the integrator Bode plot, and the differentiated Bode plot, and Bode plot of a constant. Now we're going to put them all together in terms of filters. And of course, it really, when you're going to plot a Bode plot, it really helps to know what it's supposed to look like before you jump in. And so when I look at this figure, I know I'm going to be substituting S equals J omega. But if I just look at S and go from 0, right? If I put S equals 0, then I'm going to get 10 divided by 10 times 100, right? If I let S go to infinity, this whole term goes to 0. Now, of course, you can't mix and match complex numbers like that, but it gives you the idea that it starts high, the magnitude is going to start high, and it's going to go low, right? And the shorthand for that is a low-pass filter. So before we, you're going to be doing these by hand, so you have to kind of know how to scale your axes properly. And that's relatively easy in this problem because the pole, right, is minus 10K. That means we're going to have a feature at 10K. So that means something here and something here, right? And for the phase, we have to go 1/10, and then, it's better to go 100, to set up the plot, you got to go 100th, and here you got to go 100 times that way, right? So even though I put in all this detail, I pretty much need 100 times less than the pole, or whatever, and we'll call it omega naught, divided by 100, and omega naught times 100. And what I mean by that is, let me put this generically, we can have some gain, omega naught, S plus omega naught. All right, and that omega naught is where the action will be happening. All right, so now let's do the magnitude first. And what we do is, first, now that we've got that 10K, right? So when omega is less than that pole, right, equals 10K, all right, or much, much less than that. So what happens when that H of S goes to 100 times 10K, and now this is so much less than that pole, it goes to 0. We're left with 10K. That cancels, right? And a gain of 100 gives us 40 dB.
So you're saying this is when omega is 0?
Well, it can never equal 0 because it's a
precious.
log plot, but when it's much, much less than that pole, all right? Now, what I posted online are a lot of case studies, and I really encourage you to click through everything because there's a lot of good information there. Then when it comes to a lecture, I'll do different examples so that you get even more examples. All right, so you have plenty to choose from. All right.
Could I ask you a question, Professor?
Yeah, sure.
Relative to Bode plots and the last homework, I believe some of the questions were plot a time response.
Yes.
So could you just graph a Bode plot and then flip the x-axis plot, and it would be equivalent as long as you scale the magnitude vertically?
You've been reading ahead?
Something like that. Well, I know
Okay.
like
It's
x-axis is
it's
frequency.
very I'm gonna give you two answers. In an intuitive way, yes. Okay. But in a real way to actually get the actual plot, no. All right. But what and I was going to go over this later, but what happens at low frequencies, right, on a Bode plot happens at long times on a time domain plot. And what happens at high frequencies happens at shorter times in a time domain plot. And so it's almost, but I actually show that later, but I only say it intuitively, but not a point for point equivalent plot. Okay, but that's a great question. That's really,
Okay,
really deep.
that's cool. Thank
Okay.
you.
Yeah.
I also have a quick question, not quite as deep, but why
Quite all right.
why is it equal to 40 dB? Where do we get that number?
Well, the magnitude on a Bode plot, you take 20 times the log of the magnitude, right? And the magnitude is the square root of the real part of the denominator or the numerator and the imaginary part. Well, there is no imaginary part, so we're taking the square root of 100 squared, which is 100. 20 times 100, 20 times log of 100 is 40 dB.
Awesome, thanks.
Okay, that one takes a while for it to really sink in where you don't have to think about it. Okay. Oh, yeah. Now, if you guys have created a Discord link, that's great. I just don't happen to use it. I can put that information out there if there is a link, or maybe you can just put it right here in the chat. All right. And what that last question was, is it really doesn't matter about an op-amp. It's really frequency response and time domain response was what that was really about. Okay, there we go. Okay. So now for the magnitude, again, we really only need much below the pole and much above. So now let's do omega much greater than 10K, right? So that's going to be 100 times 10K, and then it's going to be S, all right? Because S is much bigger than 10K. So this is the integrator that we have, except it's being scaled. All right. So let's do one asymptote first, and we'll just take it 40 dB. And I'm just going to draw it straight across, right? Because that's what that asymptote does. Now I've got another line, and it's going to be an integrator, and that's going to be, because it's 1 over S, minus 20 dB per decade. And it's going to equal 0 dB at 1 meg, which is off the screen. Sorry. All right. So that would be 0 dB. Oops. No, that's not. Oop, I accidentally drew it here, but the this is where it should be. Okay. Because I go over 1 decade, down 20 dB, over 1 decade, down 20 dB. And then the combined plot what I'm trying to highlight is that. Okay. So that's the magnitude. This is minus 20 dB per decade in pink. All right. Okay. Now for the phase, we have to consider when omega is a lot less than 10K, when omega is equal to 10K, and when omega is much, much bigger than that. Now the thing is the magnitudes, we only really care about the phase, not the magnitudes. But still, when omega is a lot less than 10K, HS becomes right, which is really all we care about is the phase. This is all real, so the phase is 0. So in that regime, the phase is 0. Right. When omega equals 10K, HS becomes, and here we have J 10K plus 10K. This is all real. It doesn't change with frequency. That's still 0 degrees. This gets converted to, now again, the magnitude isn't important in this case, but you can see that they're equal to each other. So the phase is 45 degrees. So 0 minus 45 gives us minus 45 degrees. Now, again, the numerator in this example doesn't change. The phase is still 0, but now we are left with j omega because omega is so much greater than 10K. So just keeping track of the phases, zero minus 90, we get minus 90 degrees of phase. So thing is with the phase, you just kind of know that for real poles and roots, right, you go a tenth. So we started off at 0. At the pole, it's minus 45. And again, this is just for a single. And then above that, it's minus 90. And you just have to just let me finish and then I'll get back any questions. Okay. And then this is the complete plot. Well, Harpreet, I appreciate your question, but that's kind of what I'm doing, at least in my mind. And if you look at the notes, I break it up into looking at to where the poles are. All right. So I'm not quite sure how to break it down any further. I appreciate your question though. But I think going through a few examples, you will start to see the process. All right.
Professor, can you
Yeah.
explain why is that in magnitude? Why is it negative 20 dB per decade?
Do you remember last week or the last time we spoke?
I still have a note.
They were in the notes. They were in the PDF notes and they were in lecture. Do you remember that or?
Not quite understanding though.
All right. Yeah. So if we look at in this regime where omega, oops. And this is for magnitude. When omega is bigger than 10K, right, the transfer function turns into 1 meg divided by S. All right. So the magnitude of the numerator doesn't change. So that's just going to be 1 meg. Right. And then this becomes omega because the magnitude equals the imaginary squared plus the real squared. In this regime, there is no real. It's all imaginary, and it's just omega, right? The imaginary number pops out, all right? So if I take 20 log of that, right, basically that becomes minus 20 log 1 meg omega. And so every decade we go over, we go down by 20.
Thank you.
Okay.
And I kind of have a conceptual question for that, Professor. Is what we're doing with that, you know, a negative amount, a negative 20 per decade, is that kind of an estimate based on when omega is much greater than 10K? Because like if omega is closer to 10K, wouldn't that not be a straight line?
Right, and that's why that's true, and that's why these are called asymptotic Bode plots.
Ah, gotcha.
And it'll be easier if I flip to an example we were going to do later. Is that here's a high pass filter, and here, right, it looks flat, and over here, you know, yeah, it looks like you have a straight line. Now, if I were to move this cursor, you can see those numbers advance very, very tiny until at some point it reaches 20 dB, but that's just because numerically the precision just starts rounding it off, right? So it is, you know, asymptotically approaching that, right? Same thing here. If I get a slope here and then take the slope here, I mean, I find the magnitude at 10, and here I'll get 20 dB, very close to 20 dB per slope. But notice you can start to see the roll off even there. So it really has to be far. But in the asymptotic Bode plot, you're kind of drawing a straight line this way. Right? And then you draw a straight line that way. And that point right there would be whatever your pole was, right? But it is an estimate. It's right at the pole, the magnitude isn't accurate at all. And it's exactly accurate for phase, right, at the pole, and then 100 times out and 100 times less. But to design and to think about it, that's really all you need. This will come up if I'm putting in a sine wave at, let's say, 20 hertz, right? And I'm not getting 20 dB gain, which my asymptotic plot would show. I'm getting something, you know, an 18 dB gain. Well, that's because of that roll off. All right. Is that good?
Yeah, thank you.
Okay. All right. So low pass and high pass. Yep, that's a pretty good summary, Javier. Okay. So now we actually have two poles to contend with. So it's takes a little bit longer to do. But if I were to plot this out, I'd make sure that I had one, right? So that means I have to draw out 100 times less than that, 100 times more than that. But then I also have 100. Well, that range is already covered. All right, so that when I'm doing my hand plot, I'd have to take into account that whole region. All right. But it's also got two zeros. At 0. All right. And so if I look at this and let S go to much, much less than 1, that means it's much, much less than 100, right? And so it's going to be S squared divided by a constant. So you're going to get a line going up, and it's going to have, we'll find that it'll be 40 dB per decade slope. Then as S goes towards infinity, right, the S's cancel out and we'll have a constant gain. So it's going to start low and then go high. All right. So omega a lot less than 1. We have S squared. S is a lot less than 1, so we're left with 1. It's a lot less than 100, so we're left with 100, right? So that's just S squared divided by 100, and this will be plus 40 dB per decade slope, all right? So you can see that that when omega equals 10, this will be 0, right? Because 10 squared is 100, right? Well, if I rewrite this in terms of 20 log omega squared 10 squared, well then I can take the exponent out, right? And I get 40 dB per decade slope. And it is going to be 0 dB when omega equals 10. No. Wait, okay, 10. when omega's in between, right, we're going to have S times 100 and now we're going to have just a 20 dB per decade slope line. And then when omega is much, much bigger than 100, we're going to have, that's bigger than 1, S is bigger than 100, S squared, that's 1, and then we're just going to get 0 dB. And it's a little trick, but it's easier for the high pass to draw them the other way. So we're at 100. We can draw our constant line. Then we have in between our 20 dB per decade slopes, right? And then we have our 40 dB per decade slopes.
Professor, did you intend to write 0 dB when omega is greater than 100? Because you wrote 10 there.
When it's much less than 1, it's going to have a 40 dB per decade slope. In between is going to be 20. And when it's greater than it's 100. And what I'm trying to show is that there's a breakpoint at 1 radian per second and a breakpoint at 100 radians per second. And you can see that the asymptote would go, along that line, but it's really only valid from here to here. Then this asymptote is really only valid from here to here, and that asymptote is only valid from there to there. If you're saying here, I'm not quite sure. I didn't
My
like
question,
that. I didn't like what I was saying there.
yeah, my question is when you're when on your left hand side, your red pen says when omega is greater than 100, it's S squared over S squared. So when we take 20 log of that, should that be 0 dB instead of 10?
Oh, this?
Yeah.
I'm not quite sure what that one is doing there. Sorry about that.
Yeah, that's one of my
Well,
question.
yeah, no, sorry about that.
S squared over S squared equals 1. That's 0.
Right, which leads to 0 dB. I mean, I could have said 1, and then that's 0 dB, but it might have been confusing where it looks like I'm saying 10 dB. That's fine. Okay. So now for the phase, you know, that your question, I had answered that and I just erased it. All right. I have things like that in the examples. And so I'm actually going to have to move on. All right. Sorry. All right. So we have the same thing. Omega a lot less than equal to 1. And here we're going to have j omega times j omega. All the imaginary parts are a lot less than the poles, so that just drops out. And because it's phase, we really don't care what the constant is. We just know that it's 0 degrees phase, right? And this way of breaking up s squared gives us 90 and 90, which then gives us 180. All right. I'm going to go a little bit differently this time and say omega a lot greater than 100, right? So we're still, s squareds are still there, but now s is much greater than that pole, s is much greater than that pole, all right? And the imaginary parts cancel out, right? And it's real, so the phase is 0. All right. Now we can also do omega equals 1, right? This is still true. And then we have well, 1 is a lot less than 100, so this part drops out. This is still going to be plus 180, but now we've got, oops, a phase of 45. All right, and that ultimately leads to this was already 45. Now that s is equal to 100, or wait, no, excuse me. When omega is much, much bigger than 1, I'm going to redraw this. I have j omega. This becomes j omega. And then this becomes 100J plus
Hey, Professor, can you scroll down a little bit, please?
sure.
Thank you.
Yeah, no, thanks for that, because sometimes I forget that I can scroll down. This is a little bit complicated, so let's just reiterate that. J omega, because in the numerator, omega is always active. It's not bigger or greater than anything. It's always there, right? So that gives 90 degrees of phase. This gives 90 degrees of phase. So it's always going to be 180. Now, let's set J equal, omega to equal to 100. Right, this is a lot bigger than that. And so 100J is a lot bigger than 1, or the magnitudes are, right? So it just becomes 100J, right? Here, $100J plus $10J, that's really we don't really care about the magnitude at this point. We're just worried about phase. So that's 45, right? Because the imaginary and the reals are equal to each other, right? So we have 180. Converting that, 100J becomes an angle of 90, right, times an angle of 45, which would combine $45. So it's really good just to put in some points and then draw it in. All right. So we know that when we're a lot bigger than 100, the phase goes to 0. Right, and that's 10 times. So the phase should be 0. Let me use a different thing. Here. All right. The phase is 180 when we're a lot less than the first pole, right, which is 10 times, so 10 times less than that. Right. Then you look at 100, at the first pole, right, we were at 135. At the second pole, we were at 4. Let me just draw a straight line through that. Okay.
Excuse me, Professor.
Yeah.
From
Excuse me?
sorry, from the omega equals 1, in the denominator with the s plus 100. Could you explain why that goes away really quick?
Which one? I'm sorry. Omega is what?
1.
Equals to 1?
Yes, equals to 1.
Okay, so I have j omega plus 1, right? But this is, oh, sorry. I have j plus 1 times j plus 100. Okay. And so this is a lot less than that, and so we can ignore it.
Okay, yeah, I was like reading an S in there, so from the writing in blue, so I was super confused about.
Sorry, S, right, S equals j omega.
Yeah,
And sometimes I'll throw them around pretty quickly because trying to get through as many examples as I can.
yeah, no, I get it. It's fine. I was just confused while reading it.
Yeah, that's, I mean, I try to show the thought process here, but then I think sometimes the notes, right, they don't have typos, but you might not understand the process. And I never did create videos for this. Okay,
Could you scroll down a bit? Oh, forget it.
sorry.
Yes. Give me a second. All right, thank you.
All right. All right. So some of these examples, this example or something very close to it, I have in the notes. Also something like that. What I wanted to make sure, even though, you know, we have 3 days of this, I kind of wanted to make sure that you had everything. So I want to skip ahead to this problem. All right. So when I'm deriving something like this, while in EE98, I might have said, well, assign your currents, assign your voltage drops, do your nodal analysis, use the internal OPAMP equation and let the gain go to infinity to solve that. It's kind of assumed that you can do that, right? And now you just know and you can just think of it, right? That's a minus sign. That really, you probably have memorized that the gain is minus R2 over R1. Well, if we just replace that with impedances, then the gain is minus Z2 over Z1. And then if we make those equivalent impedances, well, then it's just equivalent. And so you haven't really had to learn anything new, right? And then, you know, Z series, right, is just Z1 plus Z2, you know, whatever's in series, and Z in parallel is just regular parallel combinations, all right? So for me to derive it, and what I would expect you guys and eventually in 110 to do is that you say, I recognize this is an inverting amplifier, right? The gain will be Z equivalent 2 divided by Z equivalent 1, right? And you can, now, yeah, you got to assume an ideal op amp, right? But you can just recognize it. You've done that kind of derivation a lot. Yeah, so here's the thing. If you need extra help, right, on op amps in particular, well, we can set up an appointment for that. Okay. I have hinted at this, or I've kind of done this before, and I do have it in the lab manual, and I have the case studies. But again, I'm just taking a little bit of time to go over this. All right. If you need more than that, that's okay, but let's make a special appointment. So, oops. So Z equivalent 2, right, is really just R2. Z equivalent 1 is really just R1 plus 1 over SC1, right? Because ZR equals R, ZC equals 1 over SC, and ZL equals SL. All right. We have R2, and we have R1. All right. Now, the thing is while this is true, and if I were to mathematically plot out that equation, I'd get the right answer. It doesn't really put it in that pole zero format, right? And so you need things like polynomial in S in the numerator and a polynomial in S for the denominator. So you have to make that happen. It doesn't come out. So multiply through by S. All right. Pull out an R1. Oop. All right. And there's our transfer equation. Now, this is in terms of R1 and C1, and it's 1 over tau. But for Bode plots, it's really better to put it in terms of omega naught. I'm going to rewrite that. All right.
Professor, I think you meant minus R2 over R1.
Okay.
So going forward, when we solve an op amp, we're gonna mainly just gonna convert to frequency to the S domain.
It's a good question. I'm trying to think of the implications of the answer. Yeah, whenever you're gonna, I mean, of course, if the op amp has full of resistors, you don't really need that. But it would be really hard to try to do this with convolution integrals. And I'm not even going to attempt to show it. All right. It's just, it gets really messy really quickly. And even this kind of, and if you start putting gain stages together, even something like this, where you just have a buffer, right? And then you feed this into something else and try to do that in the time domain, it's very difficult. So you will, yeah, it'll be in the S domain really almost as long as you can keep it there. And then if you need to know the time domain plot, then you do the inverse Laplace transform. What can happen in 110 is we spend so much time in the S domain that sometimes you kind of forget that there is no S domain in the real world, and the only thing we have are sine waves and things that change in time and outputs that change in time. Okay. But yeah, we will basically, when we keep everything in the S domain, everything acts like a resistor, right? Except all the impedances act like resistances, except some of the impedances have frequency components to them. But the math and everything else is pretty much, or the manipulations like voltage division works just fine in the S plane. And I'll leave it at that. Right. So for an inverted op amp, for an inverting op amp, this is the equation. All right. All right, this mommy. Okay, so here is the transfer equation, and let's say R2 equals 100 kilo ohms, R1 equals 10 kilo ohms, C1 equals 1 microfarad. All right, we get all right. Okay. So for the magnitude, so really, right, this is just the first order high pass filter, right? when omega is a lot less than 10, h of s becomes minus 10 times s divided by 10, right? So then the magnitude is really minus s, or the transfer function is approximately equal to minus s, which is really the 20 dB per decade slope line, right? Because, right, the magnitude, the real part is 0. The imaginary part is minus omega, right? But we square it, take the square root, right? It's omega.
Professor?
Yes,
So I thought 1 over R1C1 should be 10 to the 1 over
Oh,
10
no.
to the negative
No,
2,
no,
so it should be 100.
it's 100.
Okay.
That's another example. Thanks, good catch. So we have a 20 dB per decade slope line, and it's 0 dB when omega equals 10. All right. The phase I have minus j omega, right, which is minus omega but the minus sign is omega minus 180. I'm going to say minus 1 has a phase of 180 times omega, which has a phase of 90, which starts us off at minus 190. All right. That's probably what you, when you have these inverting amplifiers, the phase is minus 180 out of sync. So if a first order low pass filter would go from minus 90 degrees down to 0, but when you invert it, it goes from minus 90 degrees down to 180. All right. We're running a little bit out of time. All right, so when omega is a lot bigger than 100, right, we have minus 10 s divided by s, because now we're much bigger than 100. The 100 falls out, the s's cancel. You have minus 10, which turns into 20 dB, right? And the phase, right? What's the phase of minus 10? Well, the denominator,
the
Excuse
screen.
me?
Can you scroll down for?
Oh, you can't see, okay. Hey, I mean,
I can see it fine. It might be
right, but if, listen, can you see that? Well,
Just barely.
this circle I'm drawing?
Yeah.
Okay. No, it'll give me an idea. It'll give me an idea of maybe how far to go. Anyway.
Yeah, I can see that, and I can see more on the edge too.
Yeah, it depends on the device you're viewing it on. Some mobile devices clip off the screen. You can double tap to zoom in and out maybe.
Okay.
Yeah, I'm on my mobile, and I can I can zoom out.
You're fine, Professor.
No, but I kind of assumed people were using a laptop, but now when you say mobile device, do you mean phone or iPad?
Phone or iPad. My iPad sometimes crops it.
Mm.
But usually you can zoom out. It's just not intuitive. There's no button. You just have to like magically tap and get it to work.
Okay. Because I'm kind of on a screen that's smallish as it is. All right. Oh, let's just continue. So minus 10, right, is also minus 10 divided by 1, right? And 1 is 1 with a phase of 0, right? And minus 10 is 10 minus 180 degrees. All right. So the phase is minus 180 degrees. So the area of interest is 100, right? And so down here it's 100. It's a tenth of that and 100th of that. So we come here, 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 and it was 20 dB. And then oops. Okay, now I just want to talk a little bit about how to do an exam right now. And really, all I need to know, right, to get, let's say, to get that problem correct, right, is that 1, the magnitude has that shape, and then you label that point 100 radians per second. I need to know here that the gain was 20 dB, and then you just have to draw 20 dB per decade. And really, that's all I need. It doesn't, I mean, the nicer you draw it, sure, the better, but really that's all the information that one would need to get the magnitude part of the problem correct. Right? Now here, right, you're going to have some region, right? You're going to have 100, you're going to have 1, and you're going to have 1,000. And you need that point. Right, you don't need to show the slope, but right, this was going to be 135, this was going to be minus 90, and this was going to be minus 180. So I just really need these 3 points, and it's really imperative that you plot, see how it's flat, right? It's flat and then goes down. If you draw just this, well, I don't know that you know that it's going to flatten out, right? So you have to draw beyond, all right? But that, you don't have to try to make sure that you've got a grid and you're exactly drawing 20 dB per slope. I put these things here to guide it, right? But really, you know, this is the magnitude, that's the phase, right? And that's the scale. That's pretty much it. Okay. So now let's, so this is LTspice. It's all set up. You can do a Laplace transform in LTspice. All right. And that when I run these, the circuit and the check are giving me the same, right? But what I wanted to show you before you leave is let's just take a point. Let's just take 10 Hertz. And the magnitude is 14.4 dB. And the phase is minus 121. So now if I take this, put in a sine wave of 1 amplitude, 10 Hertz, simulate that for, simulate for a second. Okay. So this is V in multiplied by 10, but then it's, why isn't it 10? Because it's being attenuated and that you can see the phase. All right, difference. So if this is the input, it looks like the phase is lagging behind, so it's negative. All right, so when I say that that Bode plot, right, if I take the magnitude of the input and divide that by the magnitude of the output and measure that phase at 10 Hertz, right? At 10 Hertz, I should get that same magnitude and phase. And what that Bode plot is like taking a sine wave and just measuring the magnitude and phase and changing the frequency and plotting it. All right. Now, you might have noticed something a little strange. is that notice it's not, notice how the sine wave isn't perfectly centered. It takes some time for that to happen. Okay, and that's because the Laplace transform, you're starting at 0. Before time equals 0, everything is 0. Where if we were using the Fourier transform, that sine wave would be there forever. So forever in this case is, you know, about a second. Okay. So we still have another day to go over this kind of thing. But I know a lot of people like to jump ahead. And so I think you should be able to do that after today. Okay. So yeah, the only thing you remember from Intro to Circuits about op amps is the inverting formula and the non-inverting formula. Right. So that you are, I'm just checking the time here. So really, right, we have impedance, which for capacitors is 1 over SC, resistances are resistances. Well, you can add impedance like adding series resistance. So you have an equivalent here, an equivalent there, and that's really just a slight modification. So that's, yeah, if you remember that, that's a great start. Then we're going to go deeper than that. Eventually, we're going to go into what happens on the inside of the op amp. But really, that for these homeworks, that's where you start. If you need more than that, I'm happy to, but you know, we got to set up a time during the week. All right. But I know that you guys got to go to 112. Yeah, people are going already. So, okay. All right. Take care.